Welcome to this groundbreaking presentation on the Gnoseological Category-Link Model based on human memory. I'm excited to introduce you to a revolutionary approach that bridges epistemological theory with practical AI applications. Today, we'll explore how Andrei Hereshchenko's innovative model, published in the international scientific journal Internauka, creates a new foundation for effective human-robot interaction systems. This research represents a significant advancement in our understanding of how human memory architecture can inform AI design, potentially transforming how we develop collaborative systems across healthcare, manufacturing, and education sectors. Current AI systems face a fundamental epistemological gap. They lack the unified cognitive framework that humans use to acquire knowledge about reality. Machine learning models operate on statistical patterns rather than the reflective, multi-stage cognition that characterizes human understanding. This creates inherently fragile human-robot interaction systems that are context-blind and unable to truly align with human cognitive processes. The critical question we must address is whether the epistemological architecture of human memory can provide the blueprint for next-generation AI systems that can effectively collaborate with humans. This slide introduces the core epistemological concepts that form the foundation of our gnoseological model. We define gnoseology as the theory of knowledge acquisition through four key categories: matter, ideal, measure, and practice. The matter category serves as the foundational layer for all cognitive processes. We highlight the critical distinction between materializing, concrete, and idealizing, abstract poles of cognition, which provides the basis for dual-mode AI reasoning. Finally, we emphasize how feedback mechanisms and comparison loops function as the engine of epistemological refinement, drawing a direct parallel to reinforcement learning cycles in AI systems. These concepts, sourced from Hereshchenko's 2024 research, establish the theoretical framework necessary for understanding the memory-based model that follows. Building on our theoretical foundation, we now present the structural innovation of Hereshchenko's gnoseological model. At its core is the different type organization of human memory's reflective capabilities. The model features four interconnected cognitive branches: strategies for macro-level goal setting, tactics for mid-level planning, positions for contextual stance, and operations for micro-level execution. Each branch occupies its own field of influence in the research/decision workflow. Unlike traditional hierarchical models, these category links form a dynamic, non-linear epistemological network that mirrors the complex, interconnected nature of human cognition. Our gnoseological model's four-stage cognition process forms a replicable AI pipeline for interdisciplinary knowledge acquisition. These stages, materializing and idealizing, informatizing and energizing, physicizing and chemicalizing, and socializing and biologizing, each process distinct aspects of reality and must operate sequentially for complete cognition. The measure-based knowledge unit system inherently detects anomalies. Deviations trigger experimental protocols, akin to AI anomaly detection. This architecture offers a template for multimodal, cross-domain AI systems to progressively refine their understanding of reality. Human memory is not merely a storage system but a reflective, multi-type organizational structure with active categorization capabilities. This architecture produces search for ideals, sequences of approaching truth, and progressive refinement loops. The direct mapping to AI systems shows long-term memory becoming knowledge graphs, working memory transforming into context windows, and reflective capabilities evolving into meta-learning mechanisms. This model's feedback comparison provides a structural template for explainable AI reasoning chains, enabling robots to truly cognize rather than just store information, distinguishing known measures from unknown phenomena dynamically. Slide 7 demonstrates the healthcare application of the gnoseological model in AI-assisted surgical scenarios. The central visualization shows a surgical robot operating within the four-stage cognitive framework. Stage 1 involves forming abstract patient health models, while Stage 3 identifies biochemical anomalies triggering experimental protocols. The strategy, tactic, position, and operation branches coordinate to align surgical goals with precise robotic actions. The gnoseological feedback loop enables post-procedure data refinement, creating a unified cognitive unit between human surgeons and robots rather than a simple tool-user relationship. This represents a paradigm shift in medical HRI systems. Slide 8 demonstrates the manufacturing application of Hereshchenko's Gnoseological model, showing how adaptive robotic assembly lines integrate Stage 2, informatizing and energizing, for continuous parameter quantification, and Stage 4, socializing, for adapting to human worker patterns. The cognition positions layer enables robots to maintain contextual stances on quality-speed trade-offs. The measurement-based decision flow shows how robots escalate to human experts when product properties fall outside standard measures, creating a practice experiment cycle. The model projects 40 to 60% reduction in quality control errors through its reflective feedback architecture, demonstrating significant industrial scalability potential. The educational AI system slide demonstrates how the Gnoseological model transforms traditional AI tutoring into a cognitively aware teaching partner. The four-stage cognition pipeline, from philosophy to mathematics, then to natural science and humanities practice, mirrors the ideal pedagogical sequence, creating a structured approach to knowledge acquisition. The memory-reflective architecture allows the AI tutor to track how students form knowledge, not just what they know, enabling personalized learning paths based on individual cognitive profiles. This application directly aligns with Hereshchenko's original goal of enhancing cognitive awareness in education systems, taking the model to global scale. The Gnoseological feedback loop continuously refines the AI's understanding of the student's epistemological state, creating truly adaptive educational experiences. This comparative analysis reveals the fundamental structural advantages of the Gnoseological model over traditional AI approaches. While standard ML and DL relies on flat statistical patterns and post hoc alignment, our model embeds epistemological refinement directly into its architecture. The hierarchical category-link network enables dynamic adaptation through measure plus experiment cycles, eliminating the need for extensive fine-tuning. Most importantly, the strategy, tactic, position, operation transparency provides explainability that standard black box models cannot match. This structural difference enables culturally adaptive AI systems that understand how different civilizations approach truth, critical for global human-robot interaction deployment. The implementation roadmap provides a structured four-phase approach to translate the Gnoseological model into practical HRI systems. Phase 1 focuses on formalizing the model as a computational ontology, establishing the theoretical foundation. Phase 2 involves developing prototype memory-reflective modules with ROS2 integration, starting with education pilots. Phase 3 expands to multi-domain testing across healthcare, manufacturing, and education with benchmarking against LLM baselines. Phase 4 aims for open-source publication and global collaboration. The key metric emphasizes cognitive alignment over simple task completion, reflecting the model's epistemological depth. This Gnoseological model represents a paradigm shift in human-robot interaction design. By using human memory's reflective organization as a precise structural blueprint rather than just a metaphor, this model provides the first epistemologically grounded framework for AI systems. The four-stage cognition process combined with the strategy, tactic, position, operation framework creates a comprehensive architecture that transcends cultural boundaries and enables true cognitive alignment between humans and robots. We invite AI researchers and data scientists to collaborate on formalizing and testing this model to unlock its full potential for creating more effective, intuitive, and socially aware robotic systems across healthcare, manufacturing, and education domains.